I'm going to talk a little bit about simple harmonic motion. Now, we did a lab prior to the lesson, and the lab was using a motion sensor and letting the logger probe plot the displacement time, velocity time, and acceleration time graphs. And this is what we ended up with. And there is a lot of physics in here. If you look at the displacement time and the acceleration time, they look like they are always opposite. Like when this one is maximum, this one is minimum. When this one is minimum, this one is maximum. Okay? And they're both kind of like at the zero at the same time. Now let's explain that. When the stretch, let's say, is at maximum, okay, the acceleration is minimum, so it's like this. So everything is going to be measured with respect to this position here, okay? So when the displacement is at maximum, which is meaning like the highest point here, okay? The acceleration, if we look at up as positive, the displacement is positive, but when you are here, you kind of like compress with respect to this other position. The force is trying to bring you down, the force of the spring on this mass. So the acceleration is in the other direction. When the displacement is down, let's call that negative, the acceleration is the other way because the force is in the other direction, and force and acceleration have the same direction, like we learned in when we did Newton's laws. Let's look at another. So in this case here, we say that the displacement and the acceleration graphs are at, there is a phase shift of pi between them, 180 degrees. When one is max, the other one is minimum. So let's look at what the velocity time graph looks like, and let's compare that, okay, with the position time graph. Okay. You see that when the position is at zero, meaning when we reach equilibrium, the velocity is maximum. And that kind of should make some sense because when you stretch it, you have all elastic potential energy. When you let go, you're losing some of that elastic potential energy, and it's becoming kinetic energy. Is this still recording?
Yeah.
Okay. So you're losing some potential energy, and it's becoming kinetic energy. When you are at the equilibrium position, which is right here, before you start going up again, there is no stretch or compression with respect to that equilibrium position. So which means there is no elastic potential energy, which means all the energy became kinetic. So it makes sense that if there is no stretch or compression with respect to the equilibrium, your speed would be at max. So that's the information we got from that video. Now, let's talk about, so we talked about the lab, and in that case with the displacement time and the velocity time, when one is max, the other one is zero, we said they are 90 degrees out of phase. So the phase shift is pi over 2. Let me just open up a Word document here so I have it blank. Okay. Okay. The position equation should look something like this, cosine theta. Now, we can use, actually I'm not going to prove this because I don't want to spend too much time on this video. So this is basically going to be A cosine 2 pi over the period times time. The velocity is going to be negative 2 pi over t, and you will learn this when you do calculus, right? A sine 2 pi over t times t, and the acceleration is just going to be negative 2 pi over t square. Just have to take my word for it. And this is x basically. So this is going to be negative 2 pi over t squared times x, and we call this quantity angular acceleration. So this is basically negative omega squared times x. Now, we're going to do F net equals ma. So your F net is based with respect to this position is negative kx. Okay, that's Hooke's law, equals ma, m, negative omega squared times x. You cross out the x's, and if you manipulate this a little more, you should get that the period equals 2 pi square root of m over k. So I'm going to write that here on the side, and we're going to look at that formula conceptually. Okay. Okay. If the mass gets bigger, the period gets bigger. So let's try that. Let's actually witness that. I have a bigger mass on my left and a smaller mass on my right. Okay. If I make them oscillate, okay, the one with the bigger mass takes longer to go back and forth. The cycle takes longer. Now, why is that? Well, this one with the heavy mass has more inertia. So once you set it in motion, it doesn't want to change. So once it starts going down, it wants to keep going down, right? It's going to resist changing and going back up. But once it's going up, it's not going to want to come back down again. This one has less inertia, so less resistance. Good. Okay. So T is proportional to the mass, actually the square root of mass. Now, if we pick a stiffer spring, right, and we do the same thing, so I'm going to remove this, the same mass, can only change one variable at a time, and I do the same thing. So this one gives me this kind of oscillations. This one is quicker, the same mass. And so which means that the stiffer the spring, right, the shorter the period, because this does it quickly. And the reason for that is because this is stiffer, so when you pull it, it has a quicker reaction. It wants to go back quickly to its equilibrium position. So that's why the period is shorter. Now, how about the amplitude? Okay? The period is not proportional to the amplitude. The amplitude has nothing to do with it, which means, and you can actually time this while I'm doing the video. So I'll give you, maybe you can time 4 cycles and compare. So I'm going to pull it just about 2 centimeters and let go. So you can time 4 cycles here, right? And get that time for 4 cycles. So you can divide it by 4 to get the period. Okay. If I pull more, right? And you can do 4 cycles here too. You should be able to get the same period. And the reason for that is if I pull a little bit, right? If I just pull a little bit from the equilibrium, okay, the distance traveled here is small, right? So people might think, well, if you pull more, isn't the distance bigger and it's going to take longer? The only difference is when you pull in more, you're traveling at higher speeds because you put in more energy into this system, mass spring system. So which means you have bigger accelerations, higher speeds. So it kind of compensates. They kind of balance out, right? So yeah, little pull, it covers less distance, but at a slower rates. More pull covers more distance, but at higher rates.